Hey guys, thanks for joining us today. Really excited for this live session that we have going on. As you can see from our title in the bottom, we're doing a live build-along session. Derrick will go a little bit more into detail as to what we're actually covering today, but I know several of you guys have already been working with him setting up your machine, so to those doing that, thank you so much for being part of our little experiment. I'm Nick. I'm the AI developer advocate at Qualcomm. You know me by now, hopefully. I've been doing a bunch of these sessions for the past about year and a half or so, and super excited to be here again. And then we have today, again, our multiple time guest, Derrick, who is a regular feature on this channel, who'll be leading this build along today. So Derrick, thanks for joining us. Great to have you.
Yeah.
And I'm excited to see what we go through today. You want to tell us a
Yes.
little more about it?
It's good to be here. Yeah. So, today, basically what we're going to do is we're going to go through, basically take you from zero to hero, getting an LLM
Nice.
DeepSeek running on our NPU. There are a couple minefields that hopefully I can navigate and avoid until the very end. So I'll also show you some known issues at the end, unless they show up while we're doing this. I'm going to try to consolidate this into an hour. Want to give a shout out to all the people on QDC. You guys have to wait a little bit while I'm get everybody else set up. Is there anybody else outside of QDC that's actually going to build along? Because that'll kind of guide things.
We'll see. I'll keep an eye on the chat if there's anyone.
Okay. So let's go ahead and just let's just get right into it. So you can see my screen.
It'll be up soon.
Oh, okay. Okay.
Is there any pre-setup that anyone needs to do just in terms of, I don't know, code or links or anything? Okay.
Yeah, let me go ahead and send this my personal repo.
Okay, cool.
I guess I'll put it here. So you can go here, follow these instructions, and that will give you all of the notebooks that we're going to go through today. You'll already also have the completed notebooks. So you'll use the one that says optimized temperature top K. Now, let me just add a caveat. These notebooks I really use for prototyping. If you want to see some beautiful, glorious commented code, that will be in the source directory.
Awesome.
In the event that we do hit a landmine, we also have a version that strictly runs on CPU. Hopefully we don't have to do that, but that's there as well.
Yeah, we're keeping it real. It happens.
So yeah, let me know when my screen starts, when my screen shows.
I do not see it. Let me check. I bet you it's the layout of the page. No, I don't see your screen. Did you click the presentation in StreamYard?
Oh, it was me. Okay, also share audio systems. Okay.
We're going to get pretty deep today while Derrick is getting this set up. I'm really excited about this one because, a lot of the ones we've done before have been, to some extent high level, but Derrick is, he's a deep dive kind of guy. So,
all right, can you see it now?
Yeah, I think so. Let me just add it to the stage and then we should be able to. Perfect. Now we're rocking.
There we go. Now I wanted to, I just kind of test drove this thing just to see what we got. And I really like the response. So, but of course this is all probabilistic, so we may not get something as good. But before we get started, I kind of wanted to show you start with the end goal. So when you get cloned this QNN sample apps, I do have a kind of a production worthy kind of system. So here you can just say enter your query, call main.py, enter your query. I'm going to say create a sonnet giving reasons why LLMs should be run locally on your personal laptop instead of in the cloud. Let's decrease these tokens. And while this is running, I'll get everybody else set up. We're going to set the temperature and we'll go through all of these in the notebook and then our top K. And then let's roll. And then we're just going to see. So now this is just saying that some of our opcodes are going to go to the CPU instead of running on our NPU. That's fine. You can see our NPU firing up. And here we go. All right. The user is asking me. So this is running on our NPU right now. So this is where we're going to get to by the end of this. And this isn't just this walkthrough won't be, we're using DeepSeek, but ideally you should be able to use any kind of any system. I mean, any LLM.
Mm-hmm.
So now for the
What did you
people
do to
that,
convert the model? Did you do anything special?
okay, so to get the model, we're working on basically, so Microsoft has this AI toolkit, and
Yeah.
basically that's where we got the models from, this AI toolkit.
Awesome.
Yeah, they provide the ONNX runtime models, and then it's just putting them. This was a really a feat in reverse engineering to get this thing to go. But I felt like we should be the pioneers with getting these models running on our NPU.
Yeah.
So if you have a
It is our
couple of
NPU,
routes you
right?
can go, exactly. You have a couple of routes, so you can go download this AI toolkit. When you do this, you'll have you'll have all of these options, and you can select the model catalog, and you can see what ONNX versions are
Mm-hmm.
available for your laptop. So if you don't have an ARM64 device, you'll only see models that are for your particular system. If you are using Snapdragon X Elite, which you should, you will see all of these models that we're going to use today.
Nice.
So, but for this build along, these are just some requirements. If you've already ran things like NumPy, if you run tokenizers on your system, you already have all of this. But I really wanted to start from, say, somebody that is getting this brand new, fresh from the start. So you'll have your
Yeah, for
Python
sure.
version, your C, C++. You have to install Visual Studio and get some desktop components. Rust tokenizers uses Rust, and then of course you need Git. Everything will be done in Git. Okay, and we finished, and it stopped in the middle of his poem. So for this particular build along, you can get the models if you want to follow along, or if you just want to git clone and run the full notebooks as is. As I said, we have this guy right
Mm-hmm.
here. If you just want to, come on, follow the instructions, get set up, download the 7B or the CPU version, put it in the right directory, and run this as is. Then you can run this and you'll get an output just as is. So that's one route. You don't necessarily have to follow along perfectly, but if you do, let's go ahead and get started. So the first thing I'm going to do is, I already have all of this here. Let me fire up a Jupyter notebook. Let me start from the beginning. You guys, QDC, you don't have to worry about this. You're already set up. So what I'm going to do is I'm going to fire up my virtual environment. And I keep a virtual environment for basically to keep everything clean. You don't want to have stuff going into your system, because things can get really, anybody that's dealt with Python a lot, things can get really nasty really quick if you don't use a virtual environment. So this is just my kind of best practices, and I always start my virtual environments with env. You can come up with your own kind of thing. And then from here, we're already in the QNN sample app. So now I'm just going to fire up this Jupyter notebook.
And as we're going along, guys, don't hesitate to leave a comment in the chat if you're following by code and you need clarification, anything like that. Derrick's going to be doing the main portion of the build along, but I'm watching to make sure we get your question answered so no one falls behind.
Yeah, unfortunately, I can't see anything that anybody is saying.
Your notebook just went off the screen. Just want to make sure that that's intentional.
Okay. Yeah.
Okay.
So this is where. Okay. So you guys, the QDC guys, you already have your system set up. I think the point that you guys are at, and we'll start here.
Before you start too, do you think you can make the text just a little bit bigger?
Yeah. Is that good?
Awesome. Yeah, yeah, it's a lot better.
Okay, so let's just call this DeepSeek build along. So the first thing that I always do here, and this is something that you can do as well, but I have all of my different environments already as a kernel. Make sure we're in environment ARM64. The very first thing that we should do is ensure that we are in fact in an ARM64, because ONNX runtime QNN will not run unless you are using ARM64. So you're not going to be on an emulated version of Python. Those instructions are also in the repo. So here we see we're ARM64, not AMD 64. So that's perfect.
They look very
Now,
similar, yes.
yeah. Now let's go ahead and we're going to do all of our imports. So we have our ONNX runtime, which is actually going to be ONNX runtime QNN, OS, of course, NumPy, some garbage collection, some PS utilities, and then of course tokenizers. Really the most important ones is going to be this guy, and this guy. These I added to
For
try
sure.
to figure out how to avoid the landmine that I'm not going to jinx
Yeah.
it.
So I just wanted to quickly just ask a question on the Python
Mhm.
environment, because I know that that can be sometimes challenging.
Yeah.
So just to confirm, you're using the Python ARM64 version in your virtual environment?
Yeah. Yep.
And what happens if somebody uses the AMD64 of Python to make their virtual environment, they
Mhm.
will not see ARM64 there, and does it automatically fall back to CPU then if they don't do
So
anything?
if they try to pip install ONNX runtime QNN and you don't
Mhm.
have an ARM64, it just won't find it. There's not going to be any wheels,
Yeah,
pre-built wheels
okay.
for it.
I've seen
So
that. Yeah.
yeah, um,
But can you
yeah, that.
do? But then from that point, right? If you just installed regular ONNX runtime
Mhm.
without the NPU, would it auto fall back to the CPU, or do you have to do something
Yeah,
different in your
yeah.
configuration?
So it should now these models that we're using are optimized for QNN. So there's
Mhm.
some opcodes that are specific to the NPU.
I
So
see.
that itself won't run on the NPU, but we do have, that other model for the CPU. All of those
Yeah, for
will
sure.
run on the CPU. But ideally,
Awesome.
technically, everything should automatically be able to fall back to the CPU if it doesn't
Yeah.
run. But there's some Hexagon specific optimizations that
Yeah.
that we've done. Um,
Okay. Cool. Yeah. Thanks for that.
so here we're still just doing what I call pipe cleaning, setting up the pipeline. So this is going to give us our root directory where all of my stuff is held. The
Mhm.
reason we need this ONNX root directory is because what's nice about when you pip install ONNX runtime QNN is it gives you all of the drivers that you need for Hexagon, for the CPU. So now that keeps you from having to go to Qualcomm's website, downloading the QNN SDK, finding the DLL. It's already there, and we can
That's
access it
awesome.
directly from pip install. So that's nice. And I think that may be the root to where some of my problems occurred because I had multiple drivers installed,
Mhm.
and I think somewhere in path, but who knows? Um, so so now I'm just saying, okay, my model subdirectory, we're going to use this 7B model. We have 4 different graphs that will be called for different parts of the inference. And then our tokenizer.json, which just does all of our mappings. It makes it real easy to go from the string to the token ID, encode,
Yeah.
decode, so on and so forth. We'll go deeper into these individual graphs as we go. So I'm just going to kind of go by here. And then we're still
Mhm.
just pipe cleaning.
Mhm.
Still pipe cleaning. So model paths, establishing all of these paths. Let's just make sure that this is actually a path. That is file. So you should see true. If you
Nice.
don't see true, then you need to go grab those models, put them in the directory, or you won't run. So I think at this point, this is where our QDC folks are. So now I'll kind of slow down a little bit, and then we'll start getting into meat of how everything goes together. So
Yeah.
the first thing that we need to do is we'll just, even though I'm not using ONNX runtime session options, I always just establish it because there's things you can do like ONNX runtime specific graph optimizations, also profiling. There's a whole ton of things that you can do. Now we get into the QNN specific provider options.
Mhm.
So the first thing we need to do, of course, is we have to point to the driver. So Hexagon DLL, which we get, as I alluded to, from this root directory and C API, and this is going to be the actual driver.
Okay.
The next thing that we can do is Hexagon can be ran in different modes. So what we're going to say is I'm going to say we want to run this thing at burst. And burst is I don't care about battery life. I want you to put everything you got at this thing. I want
Heck
the
yeah.
highest frequency. I want the highest Vmin, everything. There are other modes, and you can take this, copy this, go to our website and explore all the other options. You have high performance, which is a little bit lower mode, a little bit lower than burst. Like I said, burst is like insane, all out, go
The
crazy. Yeah,
peak Performance mode. Okay, yeah, cool.
Yep. And then you have a high performance mode, you have a sustained performance, then you have low power mode. SoC, you can get this from our website as well. And also in the blog that we'll be releasing also really goes into more details about all of these different options. So check that out if you want more information or want to know
Shout
where
out
to
to that
start to get
blog.
information. Yeah.
Yeah, that's going to come after. And guys, I've been fortunate enough to pre-read it. And let me tell you, it really goes into the lowest levels of things. And it's a very great read if you care about technical details. So definitely check that out. We'll share the link. Are we sharing it at the end of the chat or is it going live after?
That's a good question. We'll definitely share it by, we'll share it by, I'll post it on LinkedIn. And then of course, we'll do it in the Discord, hopefully by
it'll be on our
next
blogs
week.
On the Qualcomm developer. So I'll just drop that link for you. I'll just take a second to get it. And you can just come back and check out that link later on. So here's that in the chat. And I just saw, I saw a comment in our post. Timbo said this chat is quiet because everyone is focusing hard, which true.
Yeah, that's good. That's good. Yeah, I can't see anything, which is probably good because I will go on a rabbit hole quick. So anyway, so then the SoC model, we're using Snapdragon X Elite. It's SoC model 60. This, we don't need this. This is just a remnant of me trying to figure out this landmine, which I keep alluding to. I'm building up the suspense.
We'll talk about that later. Yeah.
Yeah. Profiling level. So if you want a detailed idea of how things are being delegated to the NPU, you can set your profiling level at detailed and then pass it where you want this profiling, detailed profiling to be saved. And you can see exactly how everything, the graph is being broken down and what opcodes are being delegated to the NPU. Now, this will be a huge file. I'm talking gigabytes by the time it's done for a model like this. So this is just another cool thing that you can do. And all of this is also, like I said, on this website right here, if you want to go deeper into it. We'll also do an ACP graph finalization optimization mode. We'll set this at 3. This is going to take a little bit longer to load, but the model will be more optimized. Ideally, technically, it should give us, better performance. And then this Q&A context priority is something new that they added. And this is nice because from my understanding, from reading the documents, is that this will assign, if something else tries to compete for the NPU, this will tell that the NPU scheduler, like, no, this is highest priority. Everything has to wait. So this is nice as well.
Yeah, 100%.
So we'll go ahead and set this up, and then we'll go ahead and get into our individual sessions. Okay, so we're going to get into the meat of things a little bit. So the first session that we need to set up is, of course, our embedding session. As you know, when we tokenize, so we have a string, hey, tell me how to cook a recipe. That string is going to get tokenized into token IDs. From there, we're going to pass it through our embedding layer. And what this is basically going to do, if you know dictionaries or if you look at a lookup table, it's going to go into this embedding matrix and say, hey, I need this token. I need this token. I need this token. Also give me the embedding matrix, the vector dimensions that's associated with these tokens. So that's what this first layer is going to do. Good. Yeah, that's a good sign right there. So this is where the landmine will happen if it's going to happen. So if we pass this victory, I might do a dance. So this next one is going to be this next. Actually, you know what? Let's start with this one first. I want to go in some kind of logical order. Okay. So after we have our embedding vectors, we have to do, they call it prefill, a prefill stage where we're going to say our entire initial sequence, we're going to prefill the model and get a key value cache, start getting some key value caches. So instead of doing it auto-regressively, we're going to give it all of the tokens at once and just get an initial readout of how things are working, or how things are going to go together. Probably saying that a little too hand wavy. If this one goes, we are probably, we are golden. Okay.
Sweet.
All right.
You want to
so
talk
now,
about the landmine a little later, right?
Yeah. I'm going to try to force it to happen so you can see, so that you guys don't pull your hair out if you see it. There's a lot of issues about this already on GitHub, and hopefully we can get access to the SDK so we can dig into it ourselves on our side. So now we all know that LLMs run auto-regressively. So now this particular session, I call it context iter. This will be used when we get into our auto-regressive loop to predict each token at a time. So that's pretty straightforward. Let's go with this one, please. Fingers crossed. Fingers crossed. Yes. Okay. And then, man, we are smoking right now. And then the last one, what these different context sessions will return, not only an updated key value cache, key value, query key value cache, we'll also get some hidden states. Now, what we have to do with these hidden states is we have to convert them into logits, and then that's where we'll do all the work to make our final predictions. That's what this is going to do. We're going to pass our hidden states to this head session. The output of this will be the logits, and then we'll apply our softmax, we'll apply our temperature, top K, repetition penalties, whatever else we want to do. And this is the last, this is the finale right here. Oh, yeah.
So are all of these little sessions, are they used essentially as part of a chain, or how do you, or are they used? Okay, awesome.
Yeah, we're going to link these together, and they're broken down like this because there's specific optimizations that are done for, and this is a huge model. So we can optimize things by these different graph sessions. I'm actually another rabbit hole. I would like to have it where, okay, this would be hopefully one of the only rabbit holes where I can break it down into different graphs. All the graphs that have, say, opcodes that run on CPU, they stay there because, as you know, as we move data from CPU to NPU, that's really what hurts our performance. It's not our NPU. Our NPU is a beast. It's the memory bandwidth that is going to hurt us. And it's that mem copy from CPU to NPU, from CPU to NPU is taxing. So now let's do one last thing. Let's do one last thing.
Sorry to interrupt you again. There's a couple of people in the chat that are asking about the code. Just wanted to make sure that you shared in the repo you shared already in your repo is the one that they need to get access to, the QNN sample apps, correct?
Yeah. So this one right here. GitHub.
Okay, great. Maria just shared it to the Discord chat that was created for this session. So
yeah.
So this will have another. Sorry, go ahead. Yeah.
No, I was gonna say, this has all of the notebooks also for that command line argument. And really the hope is that you guys can use this as a starting point and get to going, because all you really need to run this is all of this right here. So use this and build your products off of it, push, pull requests. But if you just want the notebooks for the walkthrough, just come here. And we also have the pose detection, just a plug for that one. But I have different things. So this one implements input-output binding. This is the one you'll run if you just want it strictly on CPU. And this is just a greedy type of sampling that we're doing.
Okay. Yeah. And the other question we got just before you move on is there any Python version dependency? I thought that you were using a specific version of Python 3.11.
Yeah. So I've tested this with 3.11, just 3.11 base. ONNX runtime QNN, it just has to be greater than 3.11. You can go, there are some dependencies. Oh no, that's PyTorch. I'm thinking about something else. Yeah, PyTorch needs it to be less than 3.13. But yeah, just do it greater than 3. Stay within 3.11 family. For this, I use 3.11, 3.11.0. I think that's a pretty good call. Paganix, you can try, 3.13.5. But generally what you see when you're working in like the machine learning space is that there are a lot of interrelated dependencies, maybe not at the top level dependencies, but down lower that require you to be on a certain version. So I always recommend you give it a shot, but you might have to downgrade. And that's another reason why we do the virtual environments, because that helps to, shift between all the different environments in case, one thing works in 3.13, another one needs 3.11. Yeah. And just a plug for a kudos to Microsoft. They actually make, if you do want to have multiple versions of Python, it used to be a nightmare to manage multiple versions of Python, but now that you can just use this command in any Python version you have, you see it here and you can create a virtual environment off of it. So like this is my emulated 3.11 emulated, 3.11 ARM 64, 3.10, and you can just easily set up a virtual environment by using whichever one you want. So that's a shout out to Microsoft, because that's very helpful.
Yeah, thanks for that. That's important. Also, one other question. Sorry we're going to get started. By the way, hi, Hamong. Great to have you on the chat. Thanks for joining us. So the other question was, which Hexagon version are you using? Is it any version, or do you have a specific one?
So for the what we're using is the one that you pip install when you install ONNX Runtime QNN.
Yeah, the QNN.
So it gives it to you. So you don't even have to worry about, oh, is this the right version? Is this one compatible? Now, maybe the landmine is caused because maybe the driver, when you update the driver, maybe there's something that goes out of sync. I don't know. But you don't have to worry about the driver itself because you'll automatically get the appropriate driver when you pip install ONNX Runtime QNN.
Yeah. So I dropped that in the chat. Obviously, it's pretty self-explanatory, but it does manage that. Also, there's another question. We're gonna have to get into this building soon, guys. But the last one, and then I'll take a pause so that Derrick can get some code running. Are you using the latest pre-alpha NPU driver available? From Qualcomm Software Center. The question is, are you using the latest pre-alpha NPU driver available on Qualcomm Software Center?
Yeah. So again, we just use what comes when you pip install ONNX Runtime QNN. So you don't have to get into all of those nuances. Now you can when you start. So that's the benefit of ONNX Runtime. I see it as is you can get something up running quick, pretty performant, and then when you need to go take something to production, then you can get into all the nuances and go to Genie and just get it as optimized as 120 tokens per second if you need. But I'd look at this runtime. It is production worthy, but it's also a prototype to see, okay, how can I make this work? So I say that to say all of those nuances with, what you're mentioning or what you're alluding to, we don't necessarily worry about that right now because the driver that we get with ONNX Runtime QNN pip install is what we get, and it's already been validated for that.
Yeah. And I would, just to add to that too, so Derrick, you can keep typing if you want, but to add, it's really, I would say, good to stick with that workflow because Microsoft is vetting a lot of the ONNX runtime stuff that gets pushed. So, it's more stable, and it can get pretty challenging once you actually get deep into the weeds, as Derrick, I'm sure, can attest to, and I can as well. Like we've gone through some of that. So
I think our goal is to get you from point A to point B as quick as possible, and then you can go down as many rabbit holes because the documentation is all there. So this is the finale. We're gonna rock and roll now. When you do this, you want to see QNN execution provider as an option. That lets you know that, hey, we are locked into our NPU and we're able to use that. So, okay, so now let's go ahead and get some fun going. So the first thing we need to do, we use this tokenizers module, and we can actually use the tokenizer.json. We'll bring that into tokenizer, and now we can use this to do all of our encoding, decoding, etc. So we'll run that. And then for the query, because I have a theme going on, this is just kind of a persona, what I call a persona. Imagine you're a cybersecurity professional, provide step-by-step reasons why AI models should be ran locally. Please consider all aspects of data privacy, cybersecurity, and then you have to kind of prompt DeepSeek to think, because LLMs are going to be ran locally, whether you believe it or not. As these models become more dense, as things get optimized, I truly believe that the future is going to be local. So here's the query, and then we're going to go ahead and encode this. So what encoding is going to do is it's going to take each one of these words, and it doesn't have to be the word per se. Sometimes it may, like, say if you have professionaling, maybe this will be 2 tokens. But for our purposes, we're just going to say it's going to tokenize each word. So we're going to take that. Now we've tokenized it. So now let's see what token IDs it gave us. Dot IDs. So for each one of these words, this is our token IDs that are associated with each one of these words. This is what the model is going to consume ultimately. Okay. So
I have another question for you. Did you do an experimentation with the prompt template that you're using? So like with and without it, I just wanted to understand, because I've noticed that some of these models, especially when we're running through ONNX Runtime QNN, they work better or worse depending on the prompt template.
There's like here. Yeah, well, yeah. So I think it's model specific. Like DeepSeek doesn't have a system prompt, and DeepSeek, from the papers that I read, doesn't like you to, like, some models, like when you first give them examples of what you want.
Exactly. Yeah.
DeepSeek doesn't necessarily like that.
Yeah,
So
because it reasons.
yeah, you kind of have to read through the papers to understand the template that you should use. I'm sure there's probably some. I'd like to read papers. I'm sure there's some. You can Google it or use your favorite LLM to understand,
Oh yeah.
how to prompt the LLM.
Yeah.
So,
And if you're here
okay.
because you like DeepSeek, that paper is actually really interesting, and it's
Mhm.
not too challenging to understand. So definitely give that a read, because it really talks about how the reasoning works and why it works, and it's there's a gold mine of information in there.
Yeah. Okay, so now we're preparing to pass this data to our embedding session. That's our first one up. But first, we need to understand what the embedding session is looking for. So we can say, okay, this is our session. I want you to get the inputs, and then I'm just going to print the name of the input of the layer, the shape of the layer, and the data type. So we know what the model expects, because if you don't pass it, the shape, and really we're just going to be doing a lot of shape shifting. I kind of coined that term with the HRNet with the pose detection one. But you have to have, you have to have these models in the shape that ONNX runtime is expecting. So now we know, okay, we need the input IDs. That's going to be this. We need the shape to be 1 by the sequence length. The sequence length is just going to be length of, let's just do
The
this.
encoding IDs, right? Yeah.
Yep. Or actually, I guess it's right here. So the sequence length is going to be that also, but 38. So our initial prompt is 38 tokens. So that's going to be what's right here. So now that I know what our session expects, now we have to manipulate this data to get it in this form, because this, as it stands right now, is not in shape 1 by 38. If we put this in a NumPy array, it would just be 38 comma
38,
something.
yeah.
So let's go ahead and use our NumPy. And this is going to take the input IDs and put it into the shape that we need it to be, as well as say, hey, I want you to cast this to data type int64. Then we'll go here. Oh, why? Oh, I missed something. Input IDs, encoding ID. Okay. Oh, okay. Easy problems. Let's just go here.
This is what happens when you type live. It's
yeah.
It's not as easy as it seems.
Input IDs. Luckily, I've barreled through this enough times that I know all of the areas except for the landmine.
Nice.
Okay, so now we see our shape is 1 by 38, 1 by sequence length. At this point, we're ready to pass through our context, our initial or our embedding layer. Sorry. Okay, so now we have our embedding session, and this is all we have to do inference. We call our embedding session, which we know is going to get delegated to the NPU or the CPU. Yeah. We're going to run this, and then this is the format. We have input IDs, and then we're going to pass our input IDs. And what we're going to get. So if you, and like I said, I'll reiterate this. If you don't have it in the proper shape, so if we just said, let me just show you an example, and hopefully I don't mess anything up with our inference, which we shouldn't. Let's go here. It's saying, hey, I don't know what kind of shape you're giving me, but this isn't what I'm expecting. He's a picky guy. So
yeah.
So let's go back here. All right, so now we have our batch length, our batch size, our sequence length, and then this embedding dimension. So remember I said when you take these tokens, you're going to basically do a lookup table and say, hey, for each one of these tokens, give me the vector embedding for each one of these tokens.
Yeah.
And if you want more detail, I would love to go in detail about this. But if you want more detail, of course, you have guy Umar, Jamil, or Andres Carpathy. They will, yeah, you can't lose.
There's really good videos. Anyone that you want to shout out, I can go grab the link for it if you want, Derrick.
Oh yeah, this Umar Jamil, he's awesome. I'm trying to channel my inner, or Andres Carpathy. So now we have our embedding output shape. This is as expected. And let's see. So now what it's saying is, okay, yeah, we have our input to our hidden states. That's one thing we're returning. We have 1 by our sequence length, which is 38, by the vector embedding. And these are going to be type float. So now, so basically I showed this to say, hey, you can find out for each layer. And right now we only have 1 layer because the embedding session is pretty simple, but you'll see it will get deep as we go. Man, okay. So I want to take a quick step back and talk about the architecture, and then we'll kind of barrel through this thing because I set a goal to complete this under an hour, but I don't know if we're going to beat that. So
it's okay if we don't.
Yeah, we'll get into some architecture stuff right now. So we already know batch size 1. Our sequence length is going to be our embedding output shape 1. So when we say, we're 0 index, so 0, 1. So I'm saying, okay, our sequence length is going to be this 38. Our hidden, our embedding vector size is going to be this. And the reason I'm establishing these is because I'm going to use these throughout the rest of the build along. Okay, so now we get into some architecture stuff. For DeepSeek, for this particular, this model, we have 28 attention heads.
Okay.
Each attention head has a size of 128. And then we have the total number of transformer layers are 28. So if we think about this from ground up, each layer, transformer layer will have 28 attention heads associated with it, each with a dimension of 128. And what ultimately is going to happen, so it's going to ultimately be a projection. So
gotcha.
We have our input sequence is going to be 1 by 38 by 3,584. Each one of these attention heads are going to get projected down to a matrix of 128.
Gotcha.
And what this is going to do is, if you're kind of familiar with convolutions, the more layers you can pick out more nuances within the picture. Essentially, it's doing the same thing, where each attention head theoretically will give maybe information about, oh, this is a noun, this is an adverb, this is so on and so forth. So we're just going to do a projection from 3,584 to 128 for each of these attention heads. And there's going to be 28 attention heads for each transformer layer. So you can do the math, 28 by 28. That's how many total attention heads you have in the entire model. So some more specific, and this is more inference related optimizations. This model uses a sliding window attention. So basically, I'm sure if you're elite code, elite code ahead, sliding window. Basically, you're only so you have 64 tokens in your context. Once you hit that max, the window is going to slide. So technically you'll start to lose context about things that happened earlier. But it actually doesn't work that way because I don't think this model is using a sliding KV cache. I don't know if that makes sense. I'm not going to go too deep into that because I need to get to this last part so we can keep going. One other specific thing that helps with inference optimization is we have only 4 key value heads. So this model uses what's called grouped query attention. So each one of our attention heads is going to always compute a query matrix, but there's going to be there's 4 KV cache heads that will be shared amongst the 28 attention heads. So we're not recomputing the key value, we're caching that, but we're not even going to compute it for each attention head. There's only going to be 4, and so basically 7 attention heads will share 1 key value head, 1 key value cache. Now I feel like I could explain that a lot better, but yeah, it's group query attention. Yeah, it's group query attention. It's an optimization to speed up inference.
Yeah, and one other question before you move on too. Which one of these, if any, are user definable, and which ones are fixed to the model?
Yeah, so so yeah, this is going to be fixed to the model.
That's what that's what I thought.
Yeah,
okay.
I believe that, and this will be also, because the 1.5B model uses 2, or the 14B model uses 2. I believe that this maybe is a inference specific. You can set this how you want, but I'm not 100% sure, so don't quote me on that. And if I'm wrong, scream in the chat. Yeah.
I'm watching. They'll call you out.
All right.
Thanks.
So as we move towards our prefill stage, let's first understand what our prefill stage expects. So once again, we're going to do this. Now we're getting into some interesting stuff because our prefill stage is going to, the inputs that it's expecting is our pass keys. And once again, now this shape is going to be 1 by our number of key value heads, our sequence length, but this is looking for our max sequence length, which is 64. So this is, yeah. So we're going to have to do some things here coming up. And then the dimensionality of our attention head. And we're going to do this for every single layer. So from 0 to every single transformer layer. So 0 to 27, we have 28 transformer layers. It starts at 0, so 0 to 27. We also have to input our hidden states, which is what we got from the embedding session, our pass sequence length, and then our total sequence length, because we need to tell the model where at you are in the inference session, especially when we get into the auto-regressive part. Now, from our embedding session, the only thing we got from our embedding session is these input hidden states. So we need to initialize our KV cache. That's what we're going to do here. So set up an empty KV cache. The shape is going to be batch size by the number of key value heads, by the max sequence length, by the attention head size. And then I'm just going to initialize it to 0. So NP zeros pass in this shape. This is going to be our pass keys. And it's going to start for all of the different layers all the way up to 27. So we'll just initialize this. We see we have 27 keys, 27 values. 28 keys, 28 values. We have a total length of 56. This is just an empty KV cache because our model expects us to pass these values. And then just a sanity check, this is what we have. It's just going to be nothing but zeros. Now, the next thing that we need to pass is we need to have this pass sequence length in this shape and our total sequence length in this shape. So we're going to, nope, not that one. We're going to go here. And then, so for our initial sequence length, it's just going to be our embedding output shape. And then, of course, indexing. So we're going to subtract 1 to get the proper index. We are expecting it to be int32. And then I reshape it to make sure that it's in this shape. And then we have our max sequence length, which is going to be 64. We're going to pass that as well, int32. There we go. And then because our inputs are our input to the prefill or context session expects it in a form of a dictionary, we have our sequence length, and we're just going to pass this here. And then we see our shape 37, 64.
Gotcha.
And then just to make sure that we have the shapes that we're expecting, our shape. This is just because I have trust issues, so I check and double check.
This is what you should be doing, right? You eventually get comfortable with it, but it's always good to run through this at least the first several times you're working on models like this.
Yep. Yeah. So now we have one more thing that we have to take care of before passing it to our prefill stage, passing it through our prefill stage. This model is expecting the shape to be 1 by 64 by 3,584. But if you remember, what we have is 38. So our sequence length was only 38. So does anybody have an answer about what we have to do? Does anybody know what we have to do next? Does it chat? Anybody
chat
answer?
Is silent.
Oh.
Bueller?
No? Okay. So we have the pad.
Tell us.
We have the pad. So, and you may say, how did you get this padding ID? So this model itself doesn't have, you can say tokenizers.padding to get the padding ID. I'm just using this end of sentence for padding. And you have, so now we're just going to say, okay, what's our embedding output shape, our padding ID. We're going to create a matrix off of that. And then we're going to say, hey, we want to pad everything after this. This is actually right padded. You can do left padding where you start with the padding and then you go to your sequence
shift it all the way over.
Yeah. Yeah. We're just going to do it this way. So now we've taken our embedding from 1 by 37 by 3,584, we brought it up to 164. This is what our model expects. Now we're almost ready to go.
Yeah.
And then just one more
So
sanity check.
when you print out the embedding, just really quickly, you're going to see then all of the the initial input that you had, and then it's going to be just a bunch of end of sentence tokens over and over again. Correct?
Yeah.
Okay.
And some say technically you should do this padding before running it through the embedding, but I kind of just do it this way. It does.
Yeah.
I haven't seen any hit on performance.
Yeah. That's one of the many points of experimentation when you're working with these. You know, if you want to try it, if you want to, you know, mileage may vary. That's the thing. All this stuff is probabilistic. So, you know, as you're working with it, if you think this isn't exactly what I want, shift it around, try something new, and you might be surprised.
Yep. Yeah. And because trust issues, let's make sure that we actually have. So I'm saying, hey, I want you to go to our sequence length +1, and I want to see this token start after our last vector embedding. So as we can see there, and then one more, let me just make sure that these match up. We see 039203. Okay, so we have our last embedding, our last token embedding, and then we see that here, and then our padding starts. We're ready to go. So last thing we need to do is we'll create the entire dictionary. So we're passing our empty KV, our sequence lengths, our padded embedding, and we're going to put it into a dictionary because this is ultimately what we need to pass to that prefill stage. We'll do this real quick. Like I said, if any of these shapes are off, this will scream at you. There we go. So now what we have is, actually, I can show you better than I can tell you, is now we will actually have the output of our hidden states, and we also have these filled KV cache values. So now it's going to be no longer 0. Now we'll actually have values here, and these will carry on. We'll continue to update this during our auto-regressive part
as you go through
to keep track of it. Yep. So these will be filled now. And what do we have our shapes. We know all of this. This shape will be, of course, we have our batch just to kind of be redundant and keep saying the same thing over and over again. Our KV heads, prompt length, and then our head dimension. Now let's store these hidden states, which is going to be at the 0 at the first index, 0 index, the first part of the list. Let's store these as just our output of our hidden states, because this is what we'll pass to our iterations stage once we get into the decoding part. And then another thing we have to do is now we need to update our KV cache. So we have the values that came out of our prefill stage. Now let's update our KV cache with these values. So we know that it starts, we know that our first index is going to, or 0 is going to be our hidden states. What we need to fill is everything from there on. So we start at 1, and then we're just going to iterate times 2, because it's going to be every other matrix, every other entry. And we're going to fill this with the pass keys from this. And if we're wondering what this is, basically it's going to, and I'm just going to put something here so we can quickly see. This is going to be our calculated key value, our key values from our prefill stage. So that's what we're going to update our KV cache with for the key pass keys, the pass values, and for every single layer. Update that. Oh, there we go right there. So pass key is going to be this guy, pass key, pass value 0, pass key 1, that, so on and so forth. Now we're getting ready to go into our head session. And we can spend a lot of time on this part, because when we get into the auto-regressive part, we're just going to be repeating this. So we're actually maybe making good time. So our head session, which is ultimately going to give us the logits, all it wants is the hidden states. So that's why I grabbed this guy. Stop, Jupiter. That's why I grabbed this here, because all it wants is this. It's just like, hey, I just want you to give me this so I can give you the logits, and then you can do your thing from there. We have to manage the KV cache ourselves. So what we want is just one layer, output hidden states, 1 by sequence length by the vector embedding, and it needs to be a float 32. And then just so we can kind of understand, oh, what is that? No, too early. Okay, yeah. Okay, so now we'll just pass our hidden states that we saw above directly to our head session, and we'll get our logits now. And then let's look at what the output is. Now our logits are going to be 1 by our sequence length, which is padded to 64, by
152,000.
Yeah, so this is going to be our entire vocabulary size.
Okay, so that's all the tokens we have available.
Yep.
As potential outputs.
Yep.
Okay.
Yeah, exactly. So every single word in the dictionary that we have vector embeddings for, it's going to be here. And this is something that we can't change either. This is based on what the model was trained on.
It's the model embeddings, yeah. Yeah. So that might change per model to model, but we're fixed for DeepSeek.
And then just for, verbosity, batch size, sequence length, vocabulary size. Okay.
Got it.
So now from these logits, let's go ahead and just talk about, real briefly talk about top K and softmax and temperature. So some of the tunable parameters that we have is what's called temperature. And how I try to build mental models for things. How I think about this is as temperature increases with anything, things start to go a little crazy. Same with your model.
Like molecules.
Yeah, exactly. So as temperature increases, okay, I'm going to go device physics because that's what I started with. As temperature increases, electrons start scattering more. Your scattering, your lattice scattering increases, starts going crazy. And during the summertime, people start losing their mind. Parties get crazy. Society gets crazy. Same with your model. As you increase the temperature, now the model may start increasing in its, I don't want to say craziness, in its chaos.
Randomness?
It'll increase the chaos. Yeah, the randomness. Thank you.
Yeah.
And what really is happening is that if we increase this temperature, then what we're actually doing is we're going to, if you think of it in terms of a histogram or a bar graph, we're going to make the probability of other token IDs, it's going to basically flatten out the probability of other token IDs being able to be selected. Versus if you lower the temperature, then some of the token IDs will have a high peak, and it's going to say, that's the one. Always, I want you to pick that one. Exactly. Or it's going to pick those very peaky probabilities. So so that's what the temperature does. And then of course we have our softmax because we need to turn this into probabilities. So that's our softmax. Top K is easier to explain without having like a visualization of it. But like I said, there's a lot of videos on this type of stuff also. So top K is going to say, okay, and I just have this initialized at 5. When you have your probabilities that we get from softmax, I want only the top 5, the top 10, and only pick from these top 10 tokens, because we're still going to have some randomness when we actually do our token selection, our next prediction selection, but we're minimizing the window from what can be selected from. So that's what we're doing here. Only pick from the top whatever tokens with the highest probability.
And those two work together. That helps keep the model, essentially in alignment. If you really want randomness, just, top K, you can do like 100 and you'll have a lot of choice for your temperature, but, it tends to help performance if it's not.
Yeah, and I've noticed with like the 1.5B models, making these more restrictive actually helps it. Versus the 7B, 14B, you can give it whatever and it's going to be pretty performant. But if you restrict these a little bit, then it actually makes the 1.5B models more coherent. And the last thing we need is this repetition penalty. Apparently DeepSeek is notorious for repeating itself. So we just do this. If you see in my total generated IDs, if you see a token that's appeared multiple times, I want you to penalize this logit by this penalization penalty. It's probably not the best way to do that, but that's how I decided to do it.
Got to make it work somehow.
Yeah.
There's always room to optimize.
And then because everybody loves a great one-liner, this is just a softmax function as one line using the lambda. And this is what I'll use in the actual model. But this is kind of more robust, so you can kind of see what's doing. Oh, and this guy, because, I didn't even talk about this. We don't want very large values. We don't want our logis that's coming in to have very large values because we are feeding it to an exponential. And if this gets large, then we're going to infinity and we can't make sense. So we're going to take the max and we're going to subtract that off just to keep, it'll increase our stability in case we encounter large logis.
Good to know.
Yep. Okay. So let's go ahead and just run. Now we're back on our prefill stage. Let's take our logis, and we only care about the last one. Add our temperature. Let's go ahead and get our next token ID. And I'm only applying a softmax here. I'm not doing top K or the repetition penalty. We got our next token ID. So what is this next token ID?
What is the next token ID, Derrick?
What did it predict? Aware. I don't know why it always predicts aware. But this is going to be the next prediction. Yeah, that's where it wants to start.
Okay.
So that's it. That's our prefill stage. That's all we need. We have our updated KV cache. We have our next token prediction. Now we can get into our auto-regressive layer. And this will be pretty quick because we've already went through all of the meat to get there. But first, let us understand what it expects. So now for our auto-regressive, our context iteration session, we only want one token. So we're only going to pass one token at a time. Of course, we need to update our sequence length, our total sequence, and then of course we need to pass our KV cache as well.
Yeah.
And that's it. So now let's.
So that makes sense. So that's going to be called, over and over to generate all tokens then.
Yep. Exactly. Yeah. So we're gonna barrel through this.
Language models demystified with Derrick.
Yeah. And I'm just gonna start do a time because I'd like to look at our our tokens per second, even though the average person can only read 5 tokens per second. So if you're at 8, 9, or 10, you're golden. But we're pushing for 120 with optimizations. So for here, I'm just gonna say max tokens 100, top K is gonna be 5. We're gonna initialize our generated IDs with this next token ID and our previous sequence length. And I actually feel like I just came across a bug that I'll allude to later. It works for now, but
so just understand quickly, you're that aware, the token that was generated at the top, that was your initial prompt that you specified earlier. It uses that to generate the next token ID, and then you start in your generation from that next token, correct?
Yep. Okay. And it has, and because it has a history of the previous KV caches, that's where it's going to be able to get the context and make the decisions off of.
Yeah. Okay.
So yeah, we're just passing it this last token ID, which I'm going to speak to something that I just thought about. This is a work in progress. The more I do this, the more I realize what's going on. So here's just some print statements. We're going to enter our auto-regressive loop. So for blank and range max tokens, now, of course, we already discussed this shape. So our input IDs, it still expects a certain shape. This is what's going to show us what we're looking at in real time. We're going to pass this input to our embedding output. We're going to get our lengths. Now we have to update our lengths. So our past sequence length is going to be what we just did, what we just had, so 64. But our total sequence length, because we're adding a new token, is now going to be +1. This is important because if you don't keep track of this and this, then your LLM is going to not know where it's at, and it's going to get stuck in a repetitive, or it's just going to talk gibberish. So this is actually very important to keep track of.
And can you remember where the previous sequence length is coming from?
Yeah, so that's going to come from what our initially, what we initially did during our prefill stage. Yeah.
Does that have anything to do with the sliding window?
So yeah, because our max sequence, remember we had to pad everything to 64 to 64, but I'm thinking now that we actually do need to do a left padding, and I'll talk about that. I'm doing a right padding I think we do need to do a left padding, and this will probably be way more performant. But I'll do a push and update to get. This is what we have right now, and it's working. So
if it ain't broke, don't fix it.
Yeah.
Classic.
So
Coding adage.
So now we do our iter inputs. We have our embedding output that we got from this guy. Our present KV, which we updated after we went through our prefill stage, and then our updated lengths. Now we're ready to pass this to our, let's just go ahead and grab all of this at once. Now we're going to pass this to our iteration, our context iter session. These inputs, remember this embedding output is only going to be 1 by 1 by 3584. So that's what it's expecting. Past this, we're going to get our hidden states from this layer, which we did above, and we're going to update our KV cache. Make that update here, because now this will get fed back into here on our next loop. Grab our logits here, what we just did above. Grab that. Let's grab the last. Let's do our logit post-processing. Logit post-processing. Let's grab our last one. We're going to apply our repetition penalty just in case. And you see here, we're passing the generated ID. So this will grow as we do more predictions. Soft max with our temperature, top K. And then we have another random choice that we pick. So that's why the top K limits, because even though we may say, hey, we have these high probabilities, there's still going to be a random choice that we're doing. So by doing top K, we're saying, I only want you to randomly pick from the tokens with the highest probability. And then we're going to append our predicted token to our generated IDs. And then we're going to update our sequence length. And
Makes sense.
We are at
that's the loop, right?
Yeah. Oh, we are at the finale now. And then let's see.
Let me know when you want the drum roll.
Yeah, here we go. Drum roll is coming. Next token ID. So if we come to this end of sentence token, I just wanted to break out the loop. You're done. In time, in minus star, get our tokens per second, and then decode the entire generated IDs.
Print the output text. Yeah. So one more quick question before we get to the final piece. That break session right there. Is that allows you to essentially break out if the model decides, hey, I'm done generating before you hit the max token sequence? Okay.
Yep. So
which is a good practice, because otherwise it can start regenerating again and it'll have a new sentence. Yeah.
So, and that's it. That's why I said we can barrel through this, because we really got through the meat above. And drum roll.
Yeah, no big deal. Just a couple. Okay, gotcha.
Let's go. Oh man. Oh, she's smoking.
There it is.
There we go. So imagine cybersecurity, and we're going to get all the reasons why, I only have 100 tokens. Dang. So we're not going to get it. But yeah, this is Jupyter Notebook. So there's going to be some latency. We're getting 10 tokens per second that we're seeing in a Jupyter Notebook. So running command line, you can imagine it will be faster. And then you take this, get your optimizations going. You can push this even higher. But the whole point that I'm trying to show is that you can, these LLMs will be ran locally. Ideally, you should be using, Qualcomm, we're already a beast. We're seeing things that are super high tokens per second. And this will give you a starting point if you just want to do some prototypes in a notebook, or if you want to go look at in my repo, look at that the source from the command line, maybe that'll give you a starting point to integrate into some of your own products, or some of your own experimentations. What else? Some other things that I'm working on that I'm going to update in the repo. You have another thing called, and this is just some inference, because my main focus is on, and I feel like us as Qualcomm, our main focus is on inference, and how do we pioneer capabilities of doing inference. Now, I didn't pioneer this speculative decoding, where basically, because we have a 1.5B model, DeepSeek model, and we have a 7B, what we can do is we can run that 1.5B model. Say we wanted to give us, give us 5 tokens. And then we can say, hey, okay, now we're going to take those 5 tokens. We're going to pass it. So what I'm doing is I'm passing it, not using this guy. I'm going to use the prefill stage, pass it there, and then validate those tokens before and then if it gets accepted, then we've got a significant improvement in our throughput, and we can increase our tokens per second significantly. So that's just another trick that's pretty cool that you can look into. And I have it done right now. There's some KV cache syncing, synchronization stuff that I'm working on. Hopefully we can get that. I can get that pushed by the end of the week. But this is the benefit of ONNX runtime also, is because you can get some experimentation. If all you care about is inference, you can take these models and do experimentation, try things. I have more ideas than I have time, and get it going. Now, let's talk about this landmine. Now, let's talk about.
Good. I was just going to ask.
Yeah. Well, let me first back up and say, I think I need to do left padding because I'm grabbing this last token ID. But I think this last token will be a padded token. So we're still able to, we're still able to do some inference because we have historical data from our KV cache, but I need to pad to the front so that the last token is actually a value. So that's something.
And then if you were using a language that read right to left instead of left to right, you would probably pad on that end.
Yeah.
Then.
Yep.
And then it would just obviously be reversed in terms of where you're grabbing the token from.
Yep. Yeah. So now the landmine. Okay. So since I have this, oh man, we survived. That was the only thing I was like stressing about. Okay. So let's see. Let me go ahead and fire up my virtual environment again.
And while Derrick is doing this, while he's typing get set up, thanks to everyone who stuck with us. We did go a little bit over time, but we're going to finish this out and we'll do a little Q&A session at the end. So of course we've been asking questions I've been trying to answer as we go, but we'll have a couple minutes at the end in case anyone has any questions.
Let's see.
And then all of this will be recorded and posted to YouTube.
Let's see what we get. Let's pick this. I have some prompts that I already used. So, but now I'm not stressed out if they don't work because I don't want you guys beating your head up against this when it's a known issue. What are some keys to happiness? And let's go to our 7B model.
Okay. So this is expected to crash, right?
Hopefully. Okay. So this thing, this
only
thing,
time you ever hear that.
Yeah, this issue it's kind of elusive, but I do know I can make it do it from here this way, but it also just shows up randomly. Okay, yeah, this is the one. This guy right here, if you see this, and there's a lot of GitHub issues on this. So now it's doing it because I have this kernel running, and this is hogging the NPU, but you will see this randomly just pop up. So like if I shut down this kernel now, it may or may not run, but you'll also see this just randomly pop up. And what I think my hypothesis, what I believe is going on, is that there's a state that's being stored on our NPU. It's running. Yeah. See, of course it wants to run now. But yeah, sometimes you'll randomly see this in back-to-back runs from main. What you have to do is sometimes just shutting down your terminal will work. Sometimes I've had to shut down the whole system to get it back up, but yeah, it gets annoying, honestly, and it's a known issue. So I'm trying to work on it and fix it.
It's one of those first generation issues that come about with these platforms. So you get a lot of power, but you have a lot of the deeper you get into the weeds, the more you might run into things. So.
So just remember, if you see this 5005 before going in the weeds, just shut down the terminal, or shut down your notebook, or maybe restart your computer, and hopefully it'll come back up. And now you can see we're getting some. You can see we're starting to get some. So this will also, as thermals improve with our next generation chips, we're throttling a little bit. Things are getting a little warm, which is why you can see we're slowing down a little bit. But then once things cool off, it'll start to jump back up. It'll start to come back up. And you can see our CPU also. But we are smoking on the NPU. And I'll run the 1.5 BC. You see it's coming back up now. And now it's started. I don't know how many.
This is a 7B, you said, right?
Yeah, this is the 7B. So I'll run it on the 1.5 B as well. And sometimes you can fresh starting the laptop, everything is cooled off. I've seen up to 20 tokens per second running 1.5. Now, of course, 1.5, you have to be more restrictive with what you ask it because it will go out in the weeds. So this was around 4.8 tokens per second. Let me just kind of showcase 1.5. And like I said, this runs as is on the, so we did a sonnet. Let's do a haiku, and then let's say model, DeepSeek 1.5B. I have some temperature. I have some. Let's see what this guy does. This one might crash, but we already made it to the end, so it is what it is. Okay, it worked. Jesus Christ. Okay, but now you can see 1.5B.
So man, you want it to crash. It doesn't crash.
Man, and I have been beating my head against this for the past month. But
we have a question from the audience, if you don't mind, while this is generating. So let's see. So the question is, how's Jupyter running here? And they said last time they tried running Jupyter on the Snapdragon laptop, there were issues with some of the dependencies. And so they ended up having to run it in VS Code. So just curious if there's anything special you did for the setup.
Yeah, no. So all you have to do, and I did just test this, all you have to do is when you clone that repo, cd git repo. Let me see, where am I at? cd QNN. And you go here, source, DeepSeek. And if you want to do HRNet pose now, there are some caveats with that one if you want to play with that one. But there's a blog for that one also. But go here, just pip install these requirements. Make sure that make sure you're using the ARM64 Python version. Pip install these requirements. So maybe there just wasn't pre-built wheels, but of course, this is still kind of new. So as time goes on, people will start building wheels specifically for ARM64. So that's probably what you ran into before. But yeah, pip install requirements.txt, and all these instructions are on the repo as well. And just fire up the Jupyter notebook, and you should be good.
Yeah.
And
let's next question after that. Thanks for that. Yeah, go for it. Well, I'll come back to the next question.
No, go ahead.
Oh, okay, cool. Last one. So the developer just realized that we're on Windows here. I'm pretty sure I know the answer, but I'll let you answer since you're the guest of honor today. Does this work on other operating systems like Ubuntu, Yocto, Linux, or Android?
Oh, so I've tried it on Windows. So I haven't. I haven't. I've tried it on Windows. I've ran it on Mac, not using these QNN optimized models, but just running on CPU, which I can probably. Yeah, that notebook is in here as well. I haven't tried it. That would be fun to do. Actually, I can probably just fire up a WSL and try to. I haven't validated it on Ubuntu, but theoretically. No, I'm not even going to say theory. I'm not going to say anything. I don't know. That's my answer. Final answer.
Yeah, that's fair. I'll add on to that too. What Derrick did specifically today is meant to target the NPU. And so the NPUs are only going to be in the essentially in the Windows on Snapdragon build. Obviously, if you potentially load up some Linux versions on there, the hardware is the same regardless of the software running on top. That said, to my knowledge, the support for it is not fully fleshed out in other operating systems. So performance may vary, and especially if you do manage to get it to run, which there's no special dependency, so it should run on Linux, for example, but you would then fall back to CPU, which would probably slow it down. So definitely explore and come back to us, Timbo, but I think Windows is where you're going to get obviously the most performance with our NPU.
Yeah. So I just added the temperature. Let's see if he starts talking. Oh, he's still doing good. So yeah,
that's great.
Yeah, like I said, you could just run this as is, play with it, add it to the entry point for this main. If you did want to, get into the weeds a little bit, is if we just kind of go into here, is just this guy. And then all of the meat, and really all you're doing is after instantiating this class, is basically calling this. And this is all of the meat and beautiful code, beautiful comments, and then unit tests and everything. So we're going to do things the right way.
That's great.
Yeah. But man, this thing is not breaking, and I'm upset. Okay, I think I can make it break. So if I stop it
And
like
this is the first time I've really been in a stream where someone's been like, man, I really want this to break right now.
yeah, because okay, now let's try this time. Either way, but yeah, that's it. Thank everybody for joining QDC. I definitely thank you guys for pioneering this. Please fill out the feedback forms. If you want, try to download your own software on there and see if Snapdragon X Elite is something that you can use in your day-to-day. If software doesn't work, yet, or if it's not as performant as you like, put that in your feedback. And I'll try to set up a meeting, find everybody's time, set up a meeting for us to actually sit down with the QDC folks and really get some good feedback. I appreciate you guys for doing that.
Yeah, and I want to make a quick shout out there too. If you're unfamiliar with QDC, because I forgot to intro at the beginning, that's our Qualcomm device cloud. I've dropped the link here in the chat, and Maria will drop it in Discord as well. But essentially, you can go to qdc.qualcomm.com, and we have a bunch of... Derrick, do you mind pulling it up quickly, just the main page of it? Yeah, so essentially you can go there and you can get access to Qualcomm devices on the cloud. So it's meant to help you with validation and test runs before you buy a platform. So of course the caveat is always you should buy your own platform for the best performance, but at least here you have a way to test, does what I want to do work on this platform? So this is just, go for it.
No, sorry, go ahead.
I was just gonna say, this is available right now for free, so you can log in and you'll get some free time when you go make an account. You just need a Qualcomm account, and the one Derrick is showing right here is our build along build that we did today. And if anybody who participated, of course, fill out the feedback forms that Derrick had, but if you found that this was useful, the hope is that we'll be able to continue with this so that as we do future build alongs, those who don't yet have an X Elite, you can actually start to feel some of the power of it, and eventually buy an X Elite, because they're great. I mean, really, it's a solid machine.
Yeah. This is the landing page for that. So this is all the people that volunteered. They started here and they had the notebook and all of the environment stuff set up already.
Yeah.
But you can also come in here. Say, I know there were some people that were asking about mobile. You have some mobile sessions that you can do. You have our RB3, so you can just go down the whatever you want to just and play with it.
Yeah. We got another question. So now's the chance. We're kind of in the last couple minutes here. We obviously went a little over time, but we'll stick around for some questions. So the question, I'll let you maybe answer first, and then if I have anything to add, then I'll add it. But it was just your take on the AI Dev Gallery app from Microsoft. Are you familiar with that?
Yeah. So that's actually, truth be told, that's where initially I got these models from. So are you talking about the AI toolkit?
No, I think they have a new one called the AI Dev Gallery. Let me go get the link.
Stuff moves so fast.
Yeah, there's a couple different ones. There's also the AI Foundry now.
But if you want, I mean, hopefully, I think Nick and I, we were discussing having a build along, maybe in the future. We have some MCP stuff if you're interested in that coming in August. So stay tuned. But we do want to do one where we take you from say Hugging Face to ONNX to optimization for NPU to running LLM. So now you can just choose whatever, we're in the talks of this. But if you do want to go the AI toolkit route, Microsoft has already provided. So here's the one that I grabbed. And if you want to know, okay, so it download, because that was a question I asked myself. I'm like, okay, this is downloading to the system somewhere. Where? I'll just run through where you find this at. You'll go to whatever your guy is here, AI toolkit, models, DeepSeek, and then whatever model that you download. And you'll just basically copy and paste this into, if you're using the repo that I developed, copy and paste it into there. And if you're using a model that isn't already there, update the JSON, put a pull request, and I'll push it in and you can use it. But they have CPU. I have a notebook that showcases how to run one of these CPU guys as well, because the models for the CPU ones is just one model. So it's actually easier than what we just went through today. So there's a notebook that shows how to go through that workflow as well.
Yeah. And I can speak. I'm familiar with the Dev Gallery to some extent, so it's definitely a good place to start, I would say, because it helps you explore all of the different possibilities. Microsoft built that specifically so that they can have, say you want to do some computer vision and you don't know what models to pick. Essentially, you go to the Dev Gallery, which again I dropped the link here in the chat. You can go and test out the models within the Dev Gallery, and when you're ready, you can actually one-click export code and mess around with the parameters, and also again one-click export the code so you can embed it directly in your app. So it's a really good starting point with this. Again, mileage may vary depending, it might be too simplistic for what you're trying to do, or you may already know how to do what it's offering. But if you're unsure, definitely check it out, because it's one of the great tools they're putting out, and there's more stuff coming from them all the time. Definitely also check out the build announcements as well, because there was a lot of cool on-device Qualcomm and Microsoft announcements, like I think it was the AI Foundry. But yeah. Okay. So we'll give it another maybe minute or two on questions. But Derrick, this was awesome, really. Did you have a favorite part about the process of doing this, or kind of what was your inspiration?
Yeah, it was really just so my inspiration is that I feel like we should be, if we have this powerful NPU, and we should be showcasing how to run these things on our NPU as easy as possible. So, honestly, the initial inspiration was I saw that Microsoft released the AI toolkit, and I'm like, okay, we need to show how to do this. But because a lot of people want to know how to run these things without going through something that's proprietary, or something that, they want to get in the weeds themselves, and then they can, come up and develop. So that was really the inspiration, to really just showcase the NPU and get a deeper understanding of LLMs from my perspective as well. So I achieved all of that, and hopefully you guys learned something, and hopefully you pull requests.
And if you need to go back, the recording is going to be there. So, keep learning. Some of the stuff maybe doesn't sink in the first time, but at least we can let it sink in, over time with a couple views. So with that, go for it.
No, I was going to say one more thing. And on our Discord server, if you have any questions, if you want me to, I'm always, looking through the Discord server. So, ask any question. If there's some things you want clarification on, you can find me there.
Yeah, we'll be in there. And like I said, if you were using one of the QDC sessions, please, the feedback is very helpful. We want to make this, again, as useful for you guys as possible. So it seemed to work pretty well. I've tested it out, and go check it out, and we'll do more of these. And actually, right as I'm signing off, we have one more question. I think it'll be good for you to shout this out, Derrick, but someone saw that there's an LLM on Edge device workshop tomorrow in San Francisco. So you want to talk a little bit about that before we sign out? That's you.
I was about to say, is that the one we're doing? Yeah. So we're so I'll be live. I'm actually flying out today, and we're basically, so I'm going to take a kind of different approach. I'm going to start with the CPU version and get it running on CPU so that people in the audience can get up and running pretty quick. But we'll go and walk through this entire thing again. So if you just want some more, you just want to, say hi in person, or the raffle, slide, come on by.
Raffle. Yeah. It'll be great. The sessions are good, and again, you can only get so much hands-on in an online, but we love doing these in-person ones. And any of the weeds you guys want to dive into, Derrick will be there to dive in with you guys. So I think this is our last one, or our second to last one.
I'm not sure.
Yeah, I think it's our second to last. I'll have to check. I've just been traveling a lot, so I'm a little bit out of it, but
jet lagged.
Yeah. Just got back from India. It's a pretty intense time zone. So, but this was, again, this was incredible. Thanks for everyone who stuck through with us. And of course, more to come from Derrick, myself, Rami, and the rest of the team supporting you guys. So as always, we'd love your feedback on, any thoughts, and we'll see you for the next one.
Yeah.
Okay.
All right.
Thanks a lot, guys. We're signing off. We'll see you for the next one. Bye.